basically derived the temperature profile and the heat flux equation in cylindrical coordinates where you have heat generation in a wire, and we refreshed our knowledge about Ohm's law, the power generated due to electricity, and so on. And we also learned how to do the correct shell balance by taking the correct shell in a different geometry than the slab geometry. And you learned that every geometry, for every geometry, there is a different type of convenient shell that you can take. So do you have any questions so far? Okay, so one thing you can do once you're done it with the solution, you should always check your answer by doing like dimensional analysis. Let me write down as a homework, check units to see whether the equation has consistent dimensionality. Okay, so make sure the left and right hand side has the Kelvin units both. Okay, so that's something you should always do. When you get an answer, you should check the units. You can also do the same thing for, you can also get, for example, like you can do different special cases. For example, you can set the heat generation to 0 to see how the temperature profile would look without any heat generation, and you can check your answer with also the solution for a temperature profile without any heat generation. Okay, good. Now let's solve the same example, but this time let's have convection at the outside of the I mean, we had convection already, but let's have insulation at the outside of the wire. Okay, so let's say this is example 2. Okay, can you hear me, by the way?
Yes.
Okay, thank you. Same example. I mean the cylindrical wire. But with a layer of insulation. On the outside. So your system is gonna look like as follows. This is your cylinder. This is the insulation layer. Again, it has a length of L. This is the insulation. And the wire has a radius of capital R again. And the outside diameter is, let's call it R1. Okay. And the insulation thickness is R1 minus R, as you can see from the schematics. The thermal conductivity of the wire was K, but of the insulation is equal to Ki. Now, when we say perfect insulation, it means the conductivity is 0. There is no conduction. But when we talk about like a commercial insulating material, it has some sort of K, but it's very small compared to for example, metals or other material. So when we say insulation, it has some sort of K, but it's going to be small. But when we say perfect insulation, that means there is no heat transfer going on there. So you can actually take the heat flux as 0, K 0, and so on. Okay. Okay. And heat transfer coefficient at insulation air interface is given as H1. Okay, so there is this air, T air, and there's this H1. Okay. So the question is now, what is the maximum temperature in the wire? Before we move on, what do you think? Is it going to be larger than we found before, or is it going to be smaller than what we found before? Numerically, although probably I'm not going to plug in numbers, but just what is your expectation? Okay, so you don't have any expectation when there is insulation. Ki, and let's call the temperature here at T1. Okay. No guess, no idea? Okay. Okay, anyway, that can be a good exam question, I guess. So shell balance, you need to do the shell balance again for the wire and for the insulating material. So you should do the shell balance for both. But the shell balance for the wire gives the same thing, right? Gives, again, because there's nothing changing within the wire. So we have the same shell balance, the same equation. So you're going to have the Q dot is equal to fancy R dot R over 2. Nothing has changed. You got the same equation. I don't need to go over this again. And the temperature profile T is going to be TR plus fancy R dot over 4K R squared minus R squared. The same as we found, but I'm not able to write TR in terms of T air. That's the only difference. But other than that, the T has the same temperature profile. But the TR might be different, but you have the same boundary condition. Although TR might be different, the T has the same functional expression. Okay? I mean, you can go ahead as an exercise and try to figure this out by using the boundary condition as at R is equal to capital R, T is equal to TR, and you would find that the same temperature dependence. Temperature depending on the radius. But how about for the insulation? For the insulating material, shell balance gives, let's do it again. Is there any guess about the Q dot? What do you think the Q dot is going to be? Remember, for the from the shell balance of the wire, we found that the Q dot was equal to fancy R dot R over 2 plus C, right? Now, what is the difference between the insulation and the wire in terms of the heat generation? Is there any heat generation in the insulation within the insulating material? Yes, no?
No.
No. So you would basically find out that in the insulation, the Q dot comes out to be constant, but let's see how it happens. Oh, I'm sorry, I did a mistake, right? It was not Q dot. What was the equation? Oops. Yeah, the equation was basically R times Q dot R squared plus C, right? To be more specific. Because C was 0 in that case, I was able to like get rid of the R's, but for the insulation, I cannot, like R is equal to 0 is not in my domain, so I cannot take the C 0, then I cannot cancel the R's. But for the insulation, the R dot is going to be 0, and you're going to find out that Q dot is equal to C over R, some constant over R. Okay, that's my expectation, but let's do it just for practice. Okay, so this is what I expect. But let's do the shell balance to see that's the case. Okay. Okay. If you do the shell balance, or maybe let's do it this way. Radius R, R plus delta R, right? And your flux is actually getting in here, QR at R, and the flux, oops, flux going out here, QR at R plus delta R. Right? And then you write the same thing in minus out plus generation is accumulation. Accumulation is 0. Very clear and easy, right? Generation is 0, and you get in minus out. Your in is basically QR times your surface area, which is basically 2 pi r L evaluated at R, minus the out is QR 2 pi r L R plus delta R. Good. Is equal to 0. Then you divide by delta R and take the limit as delta R goes to 0, and so on and so forth. And you find the following: d over dr 2 pi r L is equal to 0. But since 2 pi and L are constant, you can divide all sides by these numbers, and you get d over, and also the minus 1, d over dr. So there's one QR here. You're not warning me. QR, okay, good. QR times R is equal to 0. This tells you that QR times R does not change with R. That means QR times R is just constant. Let's call it C, and then QR comes out to be C over R, as I actually had guessed, right? That's the flux through the insulation. Okay. Any questions so far? And since I'm doing the insulation, I need to label it. This is the not the Q at any point. It's the Q through the insulation. Flux through insulation. And unlike the slab case, we have not a constant flux. It's changing with R. It's scaling with 1 over R. Okay. Now, how am I going to find C, right boundary conditions? To find C, this C I'm talking about, right? And you can say at R is equal to capital R at the insulation wire interface, the Q of the wire must be equal to Q of the insulation, correct? And the Q of the wire I already had found, right? It was fancy R dot capital R. Well, actually, it was lowercase r, but if you replace the lowercase r but by capital R, you would find that R is equal to R. Okay, divided by 2 is equal to the Q of the insulation. I found it here, right? That's C over capital R. And then I found the C as fancy R dot R squared. Let me. R squared over 2. Okay. And then now I can actually plug this in here and then find that the QR for the insulation comes out to be equal to 1 over R. Right?
So in this case, we can assume that basically the units for C is going to be joule/second meter, something like that.
Yeah, let's see. That's a great point. Thank you. And who's asking that?
Domingos?
Domingos. Excellent question, Domingos. So the units is basically, as you can see here, the R dot has the units of joules per meter cube, right? It's the heat generation, volumetric heat generation rate per unit time. And R square is meter square. So 2 doesn't have any units. So you basically have joules per meter second. And you can check it here. If you plug in here, joules per meter second, and if you divide by 1 more meter, you're going to find joule per meter square second, which is exactly the unit of the Q, which makes sense, right? Okay, good. Excellent point. So this is the QR insulation. Now, how am I going to get the temperature profile now? How am I going to get the temperature profile? Oops, so big. How am I, or let's use a more inclusive sentence, how are we able to get the temperature profile? So we need to relate Q to temperature, which is the Fourier's law. And that's basically equal to Q of the insulation is nothing but minus Ki of the insulation dt over dr. And that was equal to the QRI was found to be from here. Let's call this 1. It is, yeah, let's see what it is. Yeah. Fancy R dot R squared over 2, 1 over R. And then you solve for dt. dt comes out to be minus fancy R dot capital R squared over 2ki 1 over R dr. Take the integral, all this before the integration symbol is constant, so you can take it out of the integral. And this gives you t is equal to minus, you can either write this or you can write down the boundary. I mean, you can either write this and write down the boundary conditions, or you can just write your boundary condition exactly at this point. You can say from tr to any t, and this is from capital R to any R, and you find that t minus tr is equal to minus fancy R dot capital R squared over 2ki times the integral of 1 over R is logarithm of R, so that's logarithm of R over capital R, because logarithm of lowercase r minus logarithm of uppercase R is nothing but logarithm of lowercase r over capital R, because subtraction of 2 logarithms is the logarithm of the ratio of the 2 terms. That's it, I guess. Yeah. Okay, so you can also use the R1 as well. You can say t minus t1 is equal to, because if you use the if you take the integral from t1 to t instead of tr to t, you would get a similar formula. 2ki. This time it's going to be logarithm of r over r1. Okay. Yeah. Okay, good. So you can use either. So depending on whether you know the R1 or T1 or TR, you can actually write down either of them. So this is basically the surface. The T1 is the surface temperature, right? So you can write down the Newton's law of cooling at that surface. Apply Newton's law of cooling at the insulation air interface. And you get the flux, which is H1 T1 minus T air, is equal to the flux through the insulator at R1, which is basically, you know, the formula, fancy R dot over 2. Yeah, 1 over R1, right? I just use the equation one. Here, let me show you this equation one I used there. But I plugged in R is equal to capital R1. Okay, so this gives me a relation between T1 and T air. So instead of T1 here, I can use the air temperature. Okay, so let's solve for the T air. I'm sorry, T1. T1 minus T air comes out to be capital R, capital fancy R over 2H1 capital R1, right? Yep.
I have a question.
Yes, sure, go ahead, please.
So for in equation 1, there's the capital R squared, and I'm not seeing that.
Thank you for the correction. Who is actually correcting that?
Cameron.
Cameron, thank you so much. Excellent point. Yeah, that's the R square, exactly. And that's why you should always check the units. I mean, everybody can mess up. I can mess up. You can mess up with the when you copy things. So you should definitely check your answer by checking the consistency of the units. Yeah. I mean, the chances are, I mean, I might actually forget about it, but at the final answer, I would definitely check the units and I should realize there's a problem and I should go back and figure out that mistake. So that's always the case. I recommend you to do that as well. Okay, good. So that's T1 minus T air. We got it. And we know the here T minus T1. You can write it down here as well. T minus T1. The reason I'm writing it like minus is because I'm going to be able to like cancel those things, right? So that's why I make it in a way that I can cancel them by adding minus fancy R dot square over 2ki ln R over capital R1. And let's add the 2 to get rid of the T1 because I have no idea about what T1 is, but I have an idea about what T air is. So, so you can have T minus T air is equal to CR R square over 2H1 R1 minus fancy R dot R square over 2KI ln R over R1. Okay, good. Okay, so that's the temperature profile in the insulator, right? Okay, good. Let's check the time. Okay, so we have time still. So what was the task? What were we gonna find? What is the maximum temperature in the wire? Right now, I'm curious about the temperature in the wire. So what is the connection? What is the boundary condition or the temperature at least that actually gives me an idea of the relation of the temperature between the wire and the temperature of the insulator. So I need to find out the interface that the wire and the insulator is connected to. Okay, so I need to write down the boundary sorry, I need to relate T of the insulator to T of the wire. I had the temperature distribution for the wire already, but they are actually meeting at R is equal to capital R. So I need to write down that at R is equal to capital R, T of the insulator is equal to TR, and that's also equal to T of the wire at the meeting point, right? And you can actually write down the above formula for R is equal to capital R for the insulator, and you would find that TR minus T air is equal to, I'm going to replace the lowercase r's by capital R's. Okay, and I need to write down the equation for the wire, basically T minus TR. I would like to write the T minus TR for the wire because I want to just cancel these TRs. Okay, that's why. And from our previous analysis for the wire, have a look at this. T minus TR is nothing but this expression, correct? So I can actually plug it in here. It is fancy R dot over 4K R square minus lowercase r square. And then now you can actually add the two terms. To get rid of the TRs. And now there is nothing related to actually the TR. So T of the wire is equal to, or maybe T of the wire minus T air, but you can take T air to the right hand side. T air plus some of all the terms on the right hand side. Let's write down the constant terms first. Fancy R dot R square over 2H1 R1 minus fancy R dot R square over 2K insulator logarithm of capital R over R1 plus fancy R dot over 4K. Yeah, maybe I can expand it, or you might actually want to just keep it as this. Okay, so that's it. That's the temperature distribution of the wire. And if you want to find out the maximum temperature, Tmax, is temperature of the wire at R is equal to 0. And that's equal to T air plus that's R square over 2H1 R1 minus fancy R dot R square over 2Ki, and then R over R1 plus, and if you plug in R is equal to 0, you get that's it. That's the maximum temperature of the wire. Okay. So any questions so far? So one thing you should do, you should check your answer by doing dimensional analysis, okay, and by checking the limiting cases. Okay, for example, you can say, what if there is no insulating material, for example. You say that the R1 comes out to be equal to R, and the Ki, you don't need to talk about the Ki basically. But if you'd actually take this assumption, you would find that the, and to check whether you get the same result as before, Tmax comes out to be T air plus at R squared over 2H1 R1. Sorry, R1 is basically replaced, is going to be replaced by R. In this case, you get rid of one of the R's, minus R dot R squared over 2Ki logarithm of R over R. Logarithm of 1 is 0, so this, you get rid of this term, right? And plus that over 4K R squared. And if you actually write it in a rearranged form, if you do the simplifications, you get exactly the same thing as you found in the previous example, right? The same result as before when there were no insulators. Correct? Let's check. Was that the same? Okay, have a look at this expression. You have the T air there, fancy R dot R over 2H, fancy R dot R squared over 4K. So let's see. Yeah, it's the same equation. So that makes sense. So basically, limiting case analysis also suggests that we're not doing something actually wrong. Okay, good. Do you have any questions so far? Please say yes or no, if you can hear me.
So can you go back to the answer, because I have a question.
The previous question? The previous example?
The one that we were, no, the last example that we were working on.
Okay, yep.
Yes, so when we say there's no insulating matter, doesn't H, let me see, where is it? Doesn't K1 become just K or no?
You can
or
take the K.
H?
Yeah, no,
No,
you don't need to.
R.
Yeah, when we say there's no insulating material, you can actually, you don't need to make any assumption about the Ki, because you know that you can see that this term is actually vanishing no matter what Ki is, right?
No, I mean the term before that one, the one that has R dot R squared over 2H1. I mean that one.
Okay, so what further assumptions can you make?
Doesn't the H1 become just H?
Oh yeah, I mean it's exactly. I mean it's just the H of the air. So for the same system, it's basically not changing. Yes, because I mean this depends on the properties of the air, and it doesn't depend on whether you put an extra additional insulating material or not. So you can take the H1 as H for both problems. Okay.
Okay.